Good morning, everyone. I will present the work as chairman told, done in three universities in Lithuania, Vilnius University, Spain, University de Barcelona, and United States, Rensselaer Polytechnic Institute. Subsecond humidity sensing using surface acoustic waves in electrospray-deposited carbon nanofiber reduced graphene oxide structures. What's going about? Uh, you know, there are many humidity sensors. They are developed commercially, but most of them are very slow. They are good for certain purposes, but for example, uh, there are many applications that we need to know to measure the fast changes of humidity. One of example can be, for example, if you want to record human breathing, if you put a conventional sensor to your nostrils, you will record some integrated increase in humidity. And this is going about recording your breath out, breath in, and so on. And I can mention more applications, but motivation for selection of the method. Why surface acoustic wave? It's widely known, and it was presented several papers before, that surface acoustic waves are very sensitive to the changes in properties of the surface they propagate on, both mechanical and electrical. So this is a perfect tool to measure the changes in the properties of surface or the thin film deposited on this surface. Needless to say that actually nowadays carbon nanofibers and graphene and reduced graphene oxide films are of most interest, and there can be a separate talk about the advantages. So these materials are very promising for sensing applications, and we use a very simple electrospray technology which allows to deposit films on almost practically any surface, and what is important to us, on the surface of piezoelectric crystals. So we combine all these points of surface acoustic wave, thin layers, and we want to see what will be the result. So how the surface acoustic wave sensor works. There are two main mechanisms of response. Gravimetric response is that surface acoustic wave, which one? When you deposit a film, the velocity of surface acoustic waves propagating on the surface changes because of mass loading. The higher is mass of the layer, the lower is the velocity. We see with increasing mass, the velocity goes down. The second effect is the conductometric response, when the surface acoustic wave feels the electric property of the film. For this, you need piezoelectric crystal. When a surface acoustic wave propagates on the surface, the electric field created by acoustic wave penetrates the film, and if the film is conducting, there is a change in attenuation and in the velocity of surface acoustic wave, and this attenuation and velocity depends on the conductivity of the film, because conductivity determines the rate of the time of response. So depending how the relaxation time is compared to acoustic wave period, attenuation can reach maxima at certain conductivity, and velocity monotonically decreases when you increase the conductivity or decrease the resistance. Here is resistance maximum here. This is, and when conductivity increases, velocity goes down, and attenuation, as I told before, goes through a characteristic maximum. Method of deposition, electrospray deposition. The setup schematically is shown here. The materials or reduced graphene oxide or carbon nanofibers were dispersed in propanol, and they were deposited from a syringe through a needle, and between this needle and the electrode there was a DC electric field created. This is an image of dispersion ejection from the needle. Deposit time typically was 5 minutes, and it results in the thin layers with thickness which is very small compared to acoustic wavelength. Before the layer depositions, standard surface acoustic wave delay lines were fabricated. Here is an image of interdigital transducer. Interdigital transducers were fabricated by standard photolithography. And here we have an image of several samples with transducers and with deposited layers. The measurements were performed by measuring S parameters of the surface acoustic wave delay line using radio frequency network analyzer. So these as parameters were measured before and after layer deposition. So we see for both types of material the typical results. This is transmission dependence on frequency. This is characteristic, typical response of surface acoustic wave delay line with in transmission. This is surface acoustic wave filter with transmission at certain frequency corresponding on the period of transducers. And when the layer was deposited, we observed the decrease of transmitted wave amplitude around 7 plus minus 1 dB for both materials. What is the reason for this decrease? The first one, we can speak about just scattering, but we cannot explain this, that feed-through signal out of the acoustic transmission band is decreased very much, is strongly decreased. This decrease it implies that this is screening of electromagnetic feed-through. That means that the layer has finite conductivity. So we attribute this decrease to the acoustoelectric interaction and increase in acoustic wave attenuation. As I have shown before, attenuation depends on sheet resistance. So by measuring attenuation constant, we can solve out and extract sheet resistivity. But unfortunately, since the curve is symmetric, the result is ambiguous. There are two solutions which correspond to the same attenuation. So we can estimate the values, but we cannot tell which one is the real conductivity value in our experiment, or this or this. To give an ambiguous answer, we need to measure a phase shift because velocity changes monotonically, and so at one and at different values of sheet resistivity, the phase change would be different. But actually, the problem is that we need to separate the conductivity, the phase shift induced by acoustoelectric interaction from the phase shift induced by mass loading, mechanical effect. The simplest way is to separate this effect is to deposit the film onto metallized surface. But we did not complete this yet because this paper was accepted as a late newspaper, and we have had not much time to finish this experiment, which is on the way. So as I started to speak about humidity sensors, so we investigated the change of surface acoustic wave amplitude and phase on humidity. Very briefly, amplitude was almost constant and phase change was more pronounced. This allows us to conclude that it is mass loading effect which is responsible for observed phase changes. From this, we could estimate how the mass of absorbed moisture by each layer. So these points show the largest, correspond to the largest humidity, but we can also extract the change of absorbed moisture at any point of humidity. And finally, the time response. If we make a humidity drop, that means if we change humidity in the chamber very fast, we see that the response of surface acoustic wave is also very fast. It is it takes less than several parts of second. We cannot change faster the humidity, so our limit for the time response measurements is about 0.1, 0.2 seconds. And so we observed indeed that the surface acoustic wave delay line with nanostructural films respond very fast to humidity changes. So let me conclude that surface acoustic wave propagation and response to ambient humidity variations in carbon nanofibers and reduced graphene oxide structures was investigated. Electrospray deposition of nanostructures on YZ lithium niobate substrates introduced additional slow transmission loss, which we attributed to the acoustoelectric interaction. In both nanostructures, the slow response to humidity variation was observed. The phase response was more pronounced than the amplitude response, revealing the prevailing contribution of the mass loading effect. Rapid in the sub-second range response of the amplitude and phase to step-like humidity changes has been observed. This makes the investigated structures promising for implementation of fast SAW-based sensors. Thank you for your attention.